Okay, so we are live, Jay, and again, welcome to my YouTube channel. Anyhow, we'll just wait for some people to join. I think the live YouTube has also started. It takes some time for the notification to go, and then probably we should be able to see the people joining there.
Incredible. Hey, great to be here. I think we'll maybe start in 6 minutes, but it's an honor and a pleasure. I've seen sort of how your educational efforts over the year have sort of helped maybe millions of people.
Same goes to you. Like the kind of blogs that I've seen and the book that you have written, and that's quite amazing. So here you can see a lot of messages have started coming up now. Oh, nice. Okay.
I think we shared the same sort of passion for just learning in public, learning through teaching.
Yep.
Like I've found it to be maybe one of the most beneficial activities of my life, honestly, just to learn in public. Like you benefit from it, everybody benefits from it, and it just improves
So
everything.
here you can see some messages. Finally, Jay, I always go through your Transformer blog. So it shows it's all started with Transformer illustration blog and rest is history. So that's amazing, So let's wait another couple of minutes. If you want to probably take up any questions, we'll be happy to take that also. Um, so guys, so first of all, Jay, let's come up with a brief introduction about yourself. For people who do not know, and obviously many of them knows who are at least learning data science, machine learning, AI stuff. But definitely, anything that you want to probably introduce about yourself, give a brief background introduction, and then we can probably discuss about the agenda, how we are going to go ahead with this session.
Sounds good. So yes, great to be here. I'm Jay. I'm fascinated with machine learning. I've been in this space for close to 10 years, mostly through my blog, which started sort of introducing and explaining a lot of concepts to millions of readers. Then I worked a little bit in Udacity, where we built and rolled out the deep learning nano degree and the machine learning nano degree and created videos there. I have some lessons that I create on my YouTube channel as well. And for the last 4 years, I've been in one of the pioneering LLM companies called Cohere, where I work with a very talented team to build LLMs for both search, retrieval, classification, but also for text generation. I've been writing a book, and it just came out. It's called Hands-on Large Language Models. That's this one here. And this is written together with Martin Grotendorst, who is the creator of many NLP packages that are very popular that I've used myself, like BERT Topic, for example. So this came out in October, and we love sort of the response to it. It's a very visual introduction to let's say, the top maybe 300 intuitions and concepts people need to really understand and use LLMs successfully. It has 400 pages, but includes maybe 300 figures. And each one of these figures went through at least 7 to 10 iterations for us to really put it down to the shape. We'll be going over some of these today to explain some of the concepts that we'll be talking about in this session. And most recently, just last week, we launched a course with Andrew Ang and the folks at Deep Learning AI. It's called How Do Transformer LLMs Work? It's free. It's 90 minutes of visuals and concepts and animations as well that explain all of this. So we'd be excited if people check out all of these resources.
Sure, perfect. So guys, all the information will be given in the description of this particular video anyhow. And I think you should definitely check out the deeplearning.ai course, right, which Jay has actually come up with. So again, you can just go to deeplearning.ai and probably put that. Otherwise, I'll just give you the link, or I'll update the link in the description of this particular video. So mostly like people are here asking about multiple things. So here you can see, love Jay, Alammar blogs, attention is all you need. Like everybody probably knows you with respect to this, like fabulous work with respect to this. Then the other thing is that as Jay said, amazing book. I have also started reading that particular book, and it's really amazing how simple the words it has probably been written in. And with respect to that, you will be able to see that it has a lot of amazing contents. So definitely do check it out. All the information is given in the description. The next thing, Jay, as you said, the agenda of this particular session, like what all things you want to probably go ahead and discuss, and we can probably go ahead with that and talk more about it.
Amazing. Yes, absolutely. So we'll be talking about how LLMs are trained generally, but we'll be focusing on the reasoning LLMs. So DeepSeek R1 specifically came out. There are multiple topics about DeepSeek that different people sort of attach to. There's the consumer app. There's the sort of Chinese labs versus sort of the other international or sort of Western labs. But one of the most interesting things for me in the whole DeepSeek story is for people to be able to discuss, and for the, let's say, LLM industry to discuss things like, what are the best ways to train reasoning large language models, and then also the future for the reinforcement learning, because this was a little bit of a departure for how reinforcement learning was used traditionally. And so we'll be going over just a high-level overview of how LLMs are trained traditionally, and then we'll go into the DeepSeek R1 and see how reasoning LLMs take that a step forward, with DeepSeek as just one example, and there are others.
Perfect. I think many questions are putting. Many people are putting some different type of questions also, guys. So the session was planned. Many people had actually requested about illustrated DeepSeek R1, and I think Jay has also written a blog about it. Probably he will be taking you through that entire content, and along with that, he'll also show you some of the visuals of his books. So yes, I think Jay, we can probably start. We'll keep it till 30 minutes, I guess, and after that, we can have some Q&A and close the session.
Incredible. Sounds good. Then let me start by sharing my screen.
Yeah, sure.
Okay, and so I'm hoping people can see my screen now.
Just a second. I think this is fine. So guys, just give a confirmation if you are able to see the screen. I think I'm able to see the screen. I think so, Jay. I think it is good.
Okay, amazing. So we'll be tackling this article that I wrote. It's called the Illustrated DeepSeek R1. But before that, because like it starts out by just explaining, or the high level difference of what an R1 model looks like. So where there's a input prompt that goes into the model, and then the model sort of outputs two things: thinking component, and then, or a series of tokens, and then an answer component for the output that is generated. And to understand that, it's important to just have a initial sense of how LLMs are generally trained and how they work. So most people would know by this time that this concept of a token, where words are actually broken down into sub-word components called tokens, and the model sort of outputs them one at a time like this. And the only thing that is different in a reasoning LLMs in terms of this, let's say, mechanistic behavior, is that before answering, it takes some tokens of thinking. And so the loop for outputting the tokens spends some times where the model sort of thinks in token space. To understand a little bit, or to go a little bit into how LLMs are trained in general, we use this figure from the book, which I'll be going over here. So this is from chapter 12, where this is how you end up with, prior to reasoning LLMs. This is the general shape of how LLMs are trained. You start with an untrained model. You define a model, and then you go through the language modeling training objective. This is the predict the next token. So you have a lot of text. You give the model 5 tokens, and you hide the 6th one, and you ask the model to predict it. You know what is the correct correct token to put in there. And so the untrained model would give you a false or incorrect response, but through the training algorithm, we're able to fix the model a little bit and go through one training step where the model does that better. And that's how you end up with a model that is called a base model. And if anybody's played with open source models, for example, or some of the earlier people who've worked with models like GPT-3, for example, that is what a base model is. That's a model that has a lot of the capability, but the usage of it is a little bit difficult. Like the ways to prompt it it needs quite a bit of an advanced and maybe sometimes difficult to prompt. And so that's why this other training step, which is supervised fine-tuning or instruction tuning, is made to do. So here, the training objective is to say, okay, we'll give you a instruction, and then you will follow it. Or if we give you a question, you will be able to. If we give you an instruction, you will follow it. If we give you a question, you answer it, which is not a thing that the base models sort of reliably do. And then there's a fine-tuning or preference tuning, or what some people call RLHF, reinforcement learning from human feedback, that further polishes the output space and how short or long you want the model to output, how polite or impolite you want the model to sort of, so you can further sculpt the behavior that you want the model to have here in this step. So before getting ahead of ourselves, this figure is from chapter 12 from our book, Hands-on Large Language Models. I have a version of the book here. We'll go over a little bit of a few of the visuals on chapter 12, but we'll get to, this is a high-level overview of what the book looks like. So it's in 3 parts. The first part is just the most fundamental concepts that people need to know before they're able to use LLMs. And our bet with this book is that most people will not have to train LLMs. Most people will have to just use them and deploy pre-trained models. And so after going through the initial concepts, mainly tokenization, embeddings, and then looking at the architecture in chapter 3. So chapter 3 really is an updated version of the illustrated transformer for today. So the illustrated transformer was about 7 years ago, and that architecture has gone through, some things have changed and some things have stayed the same. And so chapter 3 talks a little bit about that architecture and how it changed. We can go through that a little bit because people already mentioned the illustrated transformer. Part 2 goes through the applications, so things you can do with a pre-trained model to solve actual world problems. So text classification, clustering, topic modeling, prompt engineering. And I was really happy that we have this chapter 5 written by Martin, who's been thinking about topic modeling with language models sort of maybe before most other folks, through building BERT topic and through supporting tens of thousands of people use BERT topic for all different kinds of applications. And we talk about advanced text generation techniques and tools. So some agentic concepts are here in chapter 7. Chapter 8, we talk about one of my favorite and one of the most applications that we see out in the wild, which is search and RAG, or retrieval augmented generation. This is where companies and users ground language models information within their own database, for example, or a certain data set. And then we talk about multimodality as well in chapter 9. Because we'll be talking about chapter 12, this is the more advanced part of the book, the third one, which is to say this is about fine-tuning, so how you fine-tune embedding models, and then how you fine-tune text generation models. Let me take you through a little bit of a glance at chapter 3, which is the updated illustrated transformer, to show you a little bit of a difference of how it is. So we begin by just showing the token by token output, and something like DeepSeek R1 does the exact same thing. So reasoning LLMs don't do this sort of any differently. This is still the same. You output one token at a time. And then the general structure of the model, which is a tokenizer and then a series of transformer blocks, and then a language modeling head, that's the same in R1. The tokenizer has a series of, or a lot of tokens in its vocabulary, and then it has token embeddings that are stored inside the model. and then the output process of calculating the probabilities and then sampling from them. This is all sort of this same as we describe here. We describe here, let's say models like, this is how models like Llama, most modern LLMs, and you will see one difference from this and to the illustrated transformer is that here we're talking specifically about decoder text generation models, which the initial transformer was an encoder-decoder structure. This one, and the most LLMs in practice right now for text generation are these decoder LLMs. And so the intro or the tutorial here goes directly through a decoder model. We also see how each token is processed in its own sort of track, and input vectors go in and go out. You can go through the book or through the illustrated transformer. Will give you these high-level ideas, but I just want to show you a little bit of a difference. So one thing that is sort of new here is the idea of performance and how it's been, over the last 7 years, maintaining or making LLMs generate tokens in a high-performance setting has been an important consideration. And so there are many optimizations that have been done on transformers. One of them is KV caching, or how you can cache previous tokens that you've generated, or the calculations and the vectors there. So generating this final token becomes faster. And so caching has been one of the developments that have been important. High-level view of a transformer block. It's still a self-attention block followed by or layer followed by a feed-forward neural network layer. A few of the things that are different here, we take another approach to visualizing attention. And attention is one of the more difficult concepts that people have to struggle with in order to really wrap their heads around transformers. And so we build new visual language to describe self-attention, and then we use it to explain the more recent advances in attention, like grouped query attention, that are used in more recent transformers. And so the high level, let's say, breakdown of this is that attention is this operation where if you're processing this token, so let's say you have the sequence of 5 tokens, and then you're processing the last one, so you're able to generate the following token. Attention is this mechanism that allows you to pull in information from the previous positions in the sequence, so as to enrich and inform this processing of this final technique. So this is a high-level sort of abstract view of attention, and then it goes through 2 steps. You break it down into relevance scoring, so looking at this token, which of the previous tokens are relevant to it, and then after scoring that relevance, we combine the information from the previous positions. We don't need to go specifically into that. Some people have heard of the KV matrices, and then we talk about sparse attention. But then here we also go into the more recent and advanced attention mechanisms like grouped query and multi-query attention, and we describe them visually. So this is a high-level overview. The last sort of figure I want to show is this. So this is the initial transformer, where how it generally looks, where you have the block and then self-attention, normalization, feed-forward neural network, and then these are this year's era of the transformer block. It looks very similar, but there's some differences. So the normalization now tends to happen before the self-attention or the feed-forward neural network, and it tends to be RMS norm. This is one of the popular methods. Attention is a little bit different. You have grouped query attention, and you have rotary embeddings. One thing that also gone missing is positional encodings no longer happen towards the beginning of the transformer. That happens in the self-attention layer, in the rotary embeddings. I can stop here to see if there are any questions, and then we can sort of continue.
Yes, guys, please, if you have any questions, do let us know. I think, Jay, no questions as such. I think you can continue.
Amazing. So this was the, let's say, high-level just preview of chapter 3 of looking inside large language models and having a sense of how they work. But then one of the important thing is to say, okay, so now we have this architecture, it's built or defined in some Python file. How do we actually train it? And that's where we can start with chapter 12. And so this is the figure that we've discussed. You begin with an untrained model, you go through base training, and then SFT or supervised fine-tuning. You'll start to come across this concept quite a bit, and when we discuss R1, you'll see how it comes together. So we have some examples here. So these are the two kinds of data sets that are used here. This is an example for instruction tuning. So this is one example for a training example, where the instruction is a question. So what are large language models? And you give the model the answer. And you train the model to answer questions when it's asked questions. If you ask a base model a question, it might answer it, but it might also give you a list of other questions that are probably similar to it. And so through instruction tuning or SFT, we guide the model to the types of behavior that we want. And the intuition is that this knowledge and these behaviors, a lot of them are present in the base model, but you use these training methods to sort of surface them and sort of bring them to the forward, rather than sort of you're teaching the model necessarily, the information that is here through instruction tuning. So these are some of the sort of intuitions. There are multiple ways of doing fine tuning. We advise people to, if you want to start with fine tuning, you should start with things that are efficient. So we talk about parameter efficient fine tuning and using adapters, for example, but also things like LoRa, and how that uses smaller matrices to be able to do fine tuning in a more efficient way than training the entire model and all of its. We talk about quantization a little bit. One thing that I want to touch on here is to just get a sense of the fine-tuning that happens towards the end there. So this is all SFT, and then preference tuning, or this is how reinforcement learning has been used to train language models before sort of these massive reinforcement learning training runs more recently. So the idea here is that you do what's called preference training. And we know that models take an input prompt and then output a generation, right? To do preference tuning, to do that RLHF, or things like an algorithm like DPO, the sense that you have, or the intuition is kind of like this. We need somebody, and this in the beginning, or a lot of the times this is a human, to be able to score a prompt. So let's say we have an input prompt that we give to a model, and the model generates a generation. We put these together and we say to a person, how good is this generation as a response to this prompt? And the person sort of gives it a preference score. It says either this is good or this is bad. This is one way of scoring these. So for us to improve the model based on this, this is what we need to do. So we need to output a generation. We need to do a preference evaluation and get a score that represents, is this a good or bad? And then based on that score, we need to go back and update the model. And this is an area where reinforcement learning from human feedback has been doing. And the preference evaluation tended to be, a lot of humans, but this is expensive. If you need tens or hundreds of thousands of preference scores, this has to be automated in some way. And so this is one area where RLHF and a lot of these other methods jumped in to help us sort of train better models through automating this evaluation. And the current or these reasoning LLMs sort of take this to the next level. So this is maybe the end of, let's say, section 1 of the recap of how LLMs are trained. And so we're going to be ready right now to jump into the next step, which is DeepSeek R1 and reasoning LLMs. I will stop again here to say if we have any questions, and then we can move forward.
So people are asking about, okay, one question that I could see. Do you see any other architecture except transformer shows comparable or better output?
Well, not yet. There aren't any other architectures that are competing with transformers in industry at the moment. There's a lot of research interest in Mamba, for example, as one possible competitive model to transformers. And I would highly recommend my co-author's visual guide to Mamba models. If you can search a visual guide to Mamba, you'll find Martin has written a highly visual intro to how that architecture works.
Okay. Where does the reinforcement learning comes? Does it conduct an FT process?
So generally, reinforcement learning happens in step 3. And there are other ways of doing it that do not require reinforcement learning. So if the second fine-tuning step tended to be where reinforcement learning from human feedback specifically, which is one form of RL, is done. But because it's RL and so a lot of these models are expensive, there have been preference tuning methods that are not necessarily as complex as a lot of the RL methods. And so you'll find methods like DPO being quite popular that require less resources to do. Because to do something like PPO, which is one of the more popular RLHF methods, it's quite expensive. Like you need different sets of the model loaded into, let's say, memory while you're doing the training process. And there are many ways where the training sort of may go wrong. And so with a lot of open source methods, you see methods like DPO sort of being used more commonly.
So one question over there by Ricky Mehra. Since DeepSeek R1 is trained using SFT and RLHF techniques, SFT makes sense as we can train our model by providing sample instruction. But how is RLHF implemented here, manually or how?
Yes, that's what we'll explain the next step. But one minor note here is that when we talk about RL within DeepSeek, we're no longer talking about RLHF. This is a different kind of RL.
True. Please continue. I think, Jay.
Okay, perfect. So we looked here at how models before reasoning LLMs were trained. So language modeling, supervised fine-tuning, and then RLHF 3 steps. Now, with models like the reasoning LLMs, they also go through the same process pretty much. So here we have a base model. So this has already gone through natural, or let's say language modeling. And then it goes through an SFT training step, and then it goes through a fine-tuning with reinforcement learning that is different from RLHF. So the high-level picture, which is good, is it's almost the same, but there are differences in how this is going. But one thing to point out here is that DeepSeek V3 base is an important model to have in the picture. So to better understand R1, it's good. There are a number of DeepSeek previous articles and models that explain these, let's say, models, architectures, and approaches that finally sort of culminate in R1. And so in the DeepSeek V3 has its own paper, and that contains, how this base model was trained and how it was fine-tuned in later steps. But here we start with the base model. Now, 3 things that are important or that make a model like, let's say, R1 a little bit different. Let me actually pull this out here to say. So 3 things. One is that the supervised fine-tuning step here, the data that we need here is quite different from traditional model SFT training, which is here you need a lot of long chain of thought examples. So these are a lot of reasoning examples that the model needs to see in its SFT. And to get this is quite difficult. And so here in the paper and the article, we discuss the approach of getting these examples. So R1 was trained on, like, the SFT component was about 800,000 training examples. 200 of them are general SFT to do, just writing or QA or other text, and then 600,000 of them were reasoning data. And it's very difficult. It was very difficult 3 months ago to find long chains of reasoning data. It's now become quite common because of efforts like this and what the open source community has been doing since this. But then the big question is, okay, how do we get these large collection of long chain of thought examples? So where you have a math problem, for example, and then you have the model think through maybe 3,000 tokens of thinking through the problem, going through dead ends, recursing back, making smaller calculations. It's like think step by step, but let's say on steroids, where there's recursion, there's backtracking, and there's breaking down a big problem into multiple subproblems and solving them. So that is done with to generate this large cache of training examples that a previous model was trained. And it could have been a check step in this process to do exactly this. And so here the paper talks about a model they call R10, and that a lot of things were learned from training this model, but a similar model to it was created in these 2 steps, let's say, of reinforcement learning. So we talked about RLHF. This is here we'll talk about a different sort of form of training these models using reinforcement learning. In R1, it happens in 2 different steps. So one is the reinforcement learning that was used to create this interim reasoning model with the purpose of generating this cache of data that we use in SFT. And then there's another reinforcement learning step that happens after the SFT to get the final R1. And so this is where the SFT or the RL, the reinforcement learning, becomes a little bit different and does things that are a little bit more interesting in how LLMs and reinforcement learning interact, and let's say different to how they have in the past. So to do that, let's talk about R10 a little bit, which is not necessarily involved in this process, but because it was developed, a lot of lessons were learned from it, and then the process was changed a little bit, and that's what led to R1. And the surprising thing here is that you can go from a base model. Using only reinforcement learning, you can create a model that is quite useful at solving reasoning problems without going through SFT. And this is a little bit sort of a departure than how LLMs are trained in the past, where SFT is needed, but they demonstrate here that you can do that. Now, how can you do that? What is different here? The difference is that reasoning problems can be verified automatically. If you have lots of prompts where the model sort of is generating a solution to a mathematical problem, and you can check the final result, or you can check the reasoning. Or if you have a model sort of that's generating code to solve a problem, you can check, you can have unit tests, you can have automatic ways and methods of verifying the model's output. If you do that, you can train a model without much human labeling or human let's say interference in that process. We give an example here. Let's say we have this prompt. So when you go into a training process like this, an RL training, you don't have what you had before. You don't have prompts, and your training data is no longer prompts and completions that are ideal like SFT. Here you go in with just a set of prompts, and then you have verifiers. So let's say you have an example like a prompt like this, which is write Python code that takes a list of numbers, returns them in sorted order, but also adds 42 at the start. So this is a mathematical, let's say it's a code reasoning problem a little bit, where there are multiple steps to it. So we can verify any output that the model generates here in several ways. So we can say, okay, we have software linter programs that can say, okay, is this Python code, or is this JavaScript, or is this just random text, or is this numbers? So here we can have a signal that, yes, the model outputted code, Python code, or let's say this is incorrect code. And then if it's actually Python code, the more we can execute the Python code to see if it even runs. So that's another signal of verifying this output. A lot of the times you have the final answer as, let's say, labeled, and you can say, okay, did the model that we execute actually give us this final result that we want or not? And then you can also generate unit tests and verify that the model generated code that satisfies all of these unit tests. So we can present an example like this, where let's say we're in training step number 1, and we have that same prompt, write a Python code that takes a list of numbers, returns them in sorted order, but also adds 42 at the start. We present that to the checkpoint that we're currently training, and then we sample multiple outputs. We don't just use, let's say, one output from the model. So let's say we get 4 out of the model, and this can be up to 16 or 64, but we'll use a simple example just to get the concept. And so the model outputs 4 different generations here. So the first one is like, here's a joke about frogs, and we know that this is not the result. The other one says, okay, echo 42, and then we have 2 other generations which are Python. We can automatically check these, and here we can say, okay, so using something like, let me maybe just zoom into this a little bit. And so we can verify, is this code? No, this is not code. So this example is let's say, is rejected somewhat. Is this code? Yes, this is code, but is this Python? No, this is not Python. So we kind of reject this example. Okay, this is a sorting method in Python. Does it pass the unit tests? Maybe it doesn't, because it didn't add or prepend the number 42. This is another function. Does it do all of these things? Let's say it does that. And so this passes the test. And so we had the prompt, we had 4 generations, 3 of them failed, 1 of them passed. So we have these scoring. So we have our reward that we can assign scores to say, okay, these 3 generations were bad, this generation was correct. And so our learning algorithm here takes this into consideration and say, okay, the next time you're solving problems like these, output more probabilities, or more, let's say, like this high reward example, and reduce the possibility or the probability of these bad example. So this is just a high level sense of how RL works. You reward the model for behaviors that you want, and you sort of penalize it or give it a lower score that then is propagated back into the weights of the model, so that these output behaviors or output outcomes change in probability. And so you do this over a long time with a lot of examples, and that's how you end up with a model like DeepSeek R1. And here are a couple of figures from the model showing as the number of steps increased, the model started doing better and better at these math problems, but also the reasoning steps, the reasoning traces. And this model has never seen reasoning, let's say, traces beyond what it's seen in the base training. It hasn't gone through an SFT for doing this. And just through these mechanisms, it through steps 4,000 or 6,000, it started generating longer and longer responses with more and more thinking tokens, and that's what enabled it, or that maybe correlates with it getting higher scores in these mathematical benchmarks. Now, the thing with R10 is that it was difficult, like its output was very specific to reasoning problems. So if you ask it a question, it wouldn't answer it, or its formatting was maybe a little bit sort of archaic. So they said, okay, we learned quite a bit from this. Let's tweak it a little bit, and that's how we get R1. And the tweak was to add a little bit of SFT, so a small step of SFT here in the beginning. So these are 5,000 examples. Some of them were labeled by humans. These are 5,000 examples of long reasoning chains for solving reasoning problems. And some of them were actually outputted by and filtered from outputs of R10. So you have these small cache of SFT, 5,000 examples. Now you have an SFT checkpoint. Then you go through the large scale reasoning-oriented RL, and that's how you have the interim reasoning model or checkpoint that is then used to create the training examples. So you use that to generate maybe 3,000 or 5,000, I don't know how many here, but then you filter those examples to find the 600,000 training examples of problem and its solution with the reasoning steps and the reasoning tokens involved. And then that's what is used for the SFT of. We looked at this, so how instruction tuning data looks like. Now, in the final step, the second step there of reinforcement learning, it's a little bit different, that it's not just reasoning focused. So R1 is able to do general copywriting and other tasks that are not reasoning tasks. And so we still have our rule-based verifiers that we used, the unit tests and the linters and the coding and the math verifiers. But for these other tasks, for writing requests or translation, there's older, let's say, regime or examples that models like Llama are trained with, of having reward models, a safety reward model and a helpfulness reward model. That's how they scored the outputs for prompts that are like general factual question answering or translation. And so for reasoning, you have one way to verify. For non-reasoning, you have this other sort of way of verify using these reward models. We finally end by talking about the architecture. So earlier in the talk, we looked at how transformer decoders are usually built. The one thing that is a little bit different in DeepSeek R1 is that it's this set of mixture of expert transformer blocks. I would highly advise going through my co-author's visual guide to mixture of experts. So this is Martin's guide for a mixture of experts. It's very detailed, extremely visual. It will explain to you sort of the main concepts of mixture of expert models and how they're used. So I would refer you to that as probably the best intro to mixture of experts. In R1, the first 3 blocks are just standard dense layers, but everything after that, up until layer 61, is a mixture of experts model. Last note on architecture is we can see a vocabulary size of about 130,000 tokens, model dimension about 7,000, transformer block dimensions about 18,000. And then they have a different paper that discusses the DeepSeek mixture of expert. I think the 2 articles are here. So this is the paper for the V3 technical report and how it's trained, and how they came up with the base model that was used here. And here's the article for the mixture of expert, which is, we signify one of the main concepts of it here is that one way that it's different or special is that you have 2 kinds of experts in each layer. You have the shared experts and the routed experts. And the shared expert is one that is always processing inputs. So this one always processes the tokens that are incoming. But from these are 256 experts. A router in the beginning of the block sort of decides which 8 experts here are best to process this token. And so that's a little bit of a departure from where you see common mixture of expert models that would generally just route through 1 or 2 or 8 experts. Again, if you'd like an intro to mixture of experts, highly recommend this article, a visual guide to mixture of experts. And so this is where we sort of conclude. This is now you should have a really good understanding of how reasoning models are trained, how they came by, how reinforcement learning is changing a little bit in how it's used in let's say, imbuing or giving capabilities to LLMs, as we saw here, to, let's say, improve the reasoning capabilities of these models. If you needed if any of these felt like advanced topics, or you needed some intros, I'd love to refer you to the book. And we have all the code examples here on GitHub. It's available for purchase on Amazon, but for the sort of readers in India, we suggest going through Shroff publishers. You'll be able to get a better deal. This is specifically for sort of our readers in India. I think this is a better deal in terms of price and let's say shipping, specifically for those readers. I hope you've enjoyed this. We're happy to take any questions. If you've gone through the book, we'd appreciate if you leave reviews. They really help us out. Thank you for listening.
So one question is that, did they train reasoning and answers differently, or are they the same COT?
So the reasoning and the answers are both part of the same generation. So they're in the SFT process, it's question and then the entire reasoning, which includes the answer and the generation. So yes, they're both let's say lumped in together in that process.
Yep. That's amazing. But I liked your entire explanation. I was able to follow each and everything. I was parallelly seeing your blog also. But this is something really amazing. So guys, if you have any questions for Jay, definitely do make sure to put it out in the chat. I will be able to highlight your questions.
Incredible.
Yeah. How is the data privacy handled, especially for sensitive information?
Like, we're discussing general, let's say, research approaches. There isn't, let's say, many details that are, let's say, necessarily relevant for that. Not that I can sort of recall from going over. Maybe you're talking about things like the DeepSeek consumer app, but the papers generally are just talking about the machine learning aspects of it, not the deployment aspects of the model.
So do you have any idea about this model, Omni-Human 1 latest China's model?
I came across it, but I didn't go into it sort of deeply. I saw some headlines.
How does Jay see the future of reinforcement learning? Is the SFT still the best way for business models?
So reinforcement learning is very exciting. It's very valuable for people to sort of focus on learning it and improving at it. SFT still has, as we saw, is still needed. It's still an important piece of the recipe. But RL at this scale is also showing, let's say, a comeback. For quite a while, RL was extremely popular. Then with the rise of LLMs, it became, a lot of the focus went to just this very small sliver of RL called RLHF. And then now there's this resurgence of RL within LLMs that is very exciting. So it's a good area to sort of focus in on as researchers and build capabilities. As we can see, sort of it improving these models.
So Jay, I usually get this question. I think I would definitely like to hear your answer. How should an organization adapt DeepSeek versus Copilot? What security vulnerabilities one has to take care between this? So
different companies, and we talk a lot with companies and enterprises, because we think about enterprise deployment of LLMs quite a bit. And so data privacy and security is one of the most important things that companies care about. And so the more, let's say, security and privacy that you get, the better for your use case. And there are some scenarios where companies have their own internal expert team that can deploy, an open source LLM on their own, let's say, infrastructure, and that's the solution for them. But a lot of companies do not have the, let's say, internal resources, because deploying a 600 billion parameter model and having it online and working efficiently for a long time, that needs a specific set of expertise. So you start to see a lot of companies relying on external companies that are LLM experts that can sort of improve and deploy these models. So Copilot is a little bit different. It's a little bit, let's say, focused on specific use cases, while DeepSeek is a general model you can use for different things. And so, yes, as a company, you need to make up sort of your own decision, looking at your own needs and requirements and what security, let's say, priorities are there for you. But I'd be remiss to sort of not also recommend sort of looking at Cohere. We think a lot about data privacy and working with enterprises to safely and securely sort of roll out LLMs for various applications.
So, Jay, just from my side, like, do you probably discuss with these things with cloud companies like AWS, GCP, like how they should probably go ahead with, let's say that you're saying, hey, one of the company wants to probably host their own open source model, and let's say they want to use their cloud. So is there any kind of talks that are happening that we can probably bring this entire deployment in a seamless way, such that no security vulnerabilities are there, in short?
Not necessarily. So I only come across sort of some companies that are trying to do that, that are focused on, let's say, deploying LLMs as a wrapper on top of AWS or on top of sort of other tools. And you see every cloud provider sort of deploying their own, version with, let's say, with their own model garden that they know can run on their hardware. And they say, okay, if you want to run this model, this is the type of instance that you sort of use. And then you see companies like Modal and others that maybe specifically work with this. So it's an area where there's a lot of work. So that's a little bit of my exposure to it, just observing the industry and how these both cloud products and cloud companies work together to serve these models.
Okay. Probably will take this question also. JEPA versus Transformer. Anything that you have?
I cannot add anything. I haven't looked deeper into JEPA.
Yeah. So guys, whatever new architecture you're asking, let him probably create an illustrated same type of blog, and then I think you should ask it. Like, it is completely different, altogether.
No, so it's and I'm sure you face this too, Chris. It's like this area, there's so much new things that happen.
Don't ask me, like, every day some new thing will become. Like, I'll be in the thought process. Okay, let me first of all explore. The space is completely new. Many things are basically coming up. So
So what is your process of? What is your process of what do you pay attention to in all of this sort of
like your like, let's say that you're focused on understanding how these things actually happens. So in my case, I have to probably make sure to understand that also, and how it is basically used in the form of applications in the company. So this is again something that I have to probably come up and think of a use case, how these specific things work as a life cycle. And when we think about applications, obviously one thing in mind will be that how do we deploy this into the cloud? How do we use it, integrate in some kind of application and all? Again, a tough task altogether, but that's okay.
Which means that you have to ignore so much more than you have to sort of pay attention to. So there's so many models coming out, so many services, and you have to be sort of really tightly focused and set your aperture, I guess, if you're like a camera, to a very small sort of point. Of things that are actually important, or things that have actually started picking up or showing results.
So that's it. Like, see, at the end of the day, everybody will ask, what is the application? How do we develop this? Nowadays, I usually get a question, hey, I have this specific use case. Can we just apply some kind of agentic AI application to solve this? And people forcefully, they will try to solve every problem with the help of agentic AI. I think that is a buzzword, In
That's
companies, it
true.
happens in that way that you have to solve a problem.
Yeah.
So try to, I don't know, like, is the investors quite interested in hearing about agentic AI, or what things are new coming in that,
Yeah. Yeah.
So they just have a word to say,
That's
like,
one
hey,
thing. Yeah.
yeah, please go ahead.
Sorry.
Mm,
That's one thing that we sort of tackle in the book, is to really solve problems. We urge people to use embedding models for a lot of use
mm,
cases, or let's say
mm,
classification models.
mm.
Instead of, yes, you can solve so many different problems with a trillion parameter generative LLMs, but you should be always thinking like an engineer and using the best tool, the most efficient tool for the job. And so at the end, yeah, you need to sort of be an engineer and focus on solving a problem with the best trade-off of resources.
Because then it comes to deployment also, because they say that, hey, we cannot share our information to anyone, so probably try to talk about those kind of deployment. That, and when I say, hey, you have to probably take care of the deployment, you have to probably do on-prem deployments,
Yeah.
make sure to have your own cloud platform or own setup. Then they'll say, we don't have that, tell us some other way. So,
True. And that's the opportunity, right? For
mm,
your viewers, for example, like they
mm,
can be the people sort of building the companies,
mm,
and they are the consultants that help companies sort of deploy these. So that friction of deploying LLMs has existed since LLM sort of started, and it's still there. And so there's a lot of room for lots of startups and companies that make that pain easy.
mm. That's it. Like, there's so many things again. And always we have to be in the toe, like something new is coming, come on, go ahead, explore it. Many
Yeah,
people are waiting for those things. That's a kind of a duty, responsibility, you can say.
true.
uh, what is the future? I think, and these all are like normal questions, I think, which I can answer specifically. So say many people are happy to see you. Yeah, I think you should do this regularly, I guess.
I appreciate it. It's an honor and a pleasure to sort of come here and discuss this with Krish.
Well, do you have any idea about LLM ops and all, Jay? So many people are
We
asking, can you? Yep.
Yeah, we haven't created sort of much on LLM ops. We tackle a little bit of maybe fine tuning and efficient fine tuning, but hopefully we can develop
Yep.
more content like that.
Perfect. Hmm. That's it. I think most of the questions are similar kind of questions that are coming up. But did you enjoy? I know, like,
Yeah, of course. No,
this,
it's
it's like what I do. One fine day, I feel like going live. I feel like doing the coding live. So many people sees that they also code along with me. So
uh,
this is the kind of process that I follow.
that's incredible. I wish I can create content sort of in this way. Like
Yeah. Yeah.
I tend to, I would love to be sort of more real time,
Mm,
but like it's my zone is to reiterate on a thing, like create it, revise it. Like even my
mm,
videos, like I would, go over
mm.
a few revisions. But I've always sort of wanted to be a little bit more real time, and I think you do it incredibly well. So I truly enjoyed this.
I say that if I'm making mistake, please ignore it. That's it. That is the best thing. Then, and it's like that, right? If you keep on teaching something live, right? Many people will have different questions. Then you get to know about the topic much more well.
100%.
That that
Learning on public, it's the best life skill.
yep. Yep. Okay, perfect. So Jay, I won't take most of your time. Like it's more than 1 hour right now. So I hope you enjoyed this. Thank you for again coming over here, spending your 1 hour precious time to the audience itself. And obviously teaching the entire thing of DeepSeek R1, probably going through it. Definitely go ahead and check out Jay videos in YouTube channel, book. All the information will be given in the description of this particular video. And Jay, let's plan for something else similarly, and let's do some amazing thing in the future, right? And do you
Absolutely.
have any message for the audience? Anything that you want to say?
Thank you so much. It's been a delight sort of coming in and speaking. Yes, absolutely. Like we'll discuss the next major model that comes out next week and sort of breaks stock market again. But my general recommendation to people is to continue learning in public themselves. And so anything that you learn, any experiments that you do, think about writing a short blog post or a short YouTube video or a short tweet or post on LinkedIn, and we continue to sort of improve and learn and teach each other and share what we learn. That's always been the most beneficial thing that I've done. And so I encourage people to continue doing that and help others become better and better at these technologies.
Perfect. Thank you, Jay. And one last question, I think. Chris, sir, please ask, what's the future of transformer architecture beyond LLM? What's the future of AI beyond LLMs? So many people are talking about AGI nowadays, right? So,
yeah, it's one area that's been fascinating for me is how multiple modalities have been shrunk into the formulation of a transformer and tokens, and that has been sort of quite fascinating to see a transformer language model now become a vision language model, or a VLM, because you can represent images and then videos as tokens as well as audio. And so that's one area there's quite a bit of very smart, let's say, engineering and representation modeling that happened there to enable the same model to input and maybe in the future output, I don't know, multiple modalities. So I think multimodalities, in addition to RL that we've discussed, these are fascinating area that at least for the next couple of years will be very exciting.
Amazing. So thank you, Jay, again for this amazing session. We'll definitely plan something for the future, but again, because of time constraint, as I will keep it short till 1 hour. That was the plan. So thank you everyone for attending, and again, thank you, Jay. We'll have this session again, definitely, for sure. I will be closing the live stream, guys. And other than that, you can check out all the information regarding Jay's social media handling channel, YouTube channel, book, everything in the description of this particular video. This was it from our side. Thank you, everyone. Take care. Have a great day and keep on rocking. Thank you, Jay.
Thank you.